to work this time, huh? Okay, there we go. So this is question number 7. It deals with the common ion effect and how a common ion affects solubility. So it says you've got a saturated solution of magnesium hydroxide. It's got a pH of 10.50, and it asks you to calculate the solubility of magnesium hydroxide in a barium hydroxide solution with a pH of 12.60. So let's start with the first part. The first part tells us that in our saturated solution, right, which is going to be related to our KSP, right? KSP is for a saturated solution of magnesium hydroxide. We've got a pH of 10.50. So that means when you take your magnesium hydroxide, which is a solid, it's going to be in equilibrium with magnesium cations and 2 hydroxide ions. Now, initially, you start out with some magnesium. We don't worry about the concentration because it's solid. It doesn't have a concentration. We don't have any of these, but we know that some of that is going to dissociate. We're going to form some magnesium ions, but we're going to form twice the amount of hydroxide ions. Again, we ignore the concentration of our magnesium hydroxide, but at equilibrium, when KSP is achieved, the saturated solution, we have X for a concentration of magnesium, and we have 2X for our concentration of our hydroxide. Now, can we calculate the concentration of the hydroxide? The answer is yes, because we have the pH. If the pH is equal to 10.50, that means that the pOH is going to be equal to 14 minus 10.50, which equals 3.50. And if we want to figure out the concentration of hydroxide, it's going to be equal to 10 to the negative pOH, which is equal to 10 to the negative 3.50. And therefore, the concentration of our hydroxide, which is 2X, is going to be equal to 3.2 times 10 to the negative 4 molar. Now, if that is equal to 2X, that means the X is going to be equal to 3.2 times 10 to the negative 4 molar divided by 2, which is going to be equal to 1.6 times 10 to the negative 4 molar. So now I have the concentration of my magnesium ions, and I have the concentration of my hydroxide ions. Now I can write out an expression for KSP. My KSP is going to be equal to the concentration of my magnesium ions times the concentration of my hydroxide ions squared. I know both of those concentrations, and so now I can calculate a KSP, which wasn't given to me. Okay, you've got to be able to read this problem and say, well, I need to calculate KSP first before I can determine the solubility of the magnesium hydroxide in the solution with a pH of 12.60. So we put in our numbers, 1.6 times 10 to the negative 4 multiplied by 3.2 times 10 to the negative 4 squared. And when you put all that in your calculator, you get that your KSP is equal to 1.6 times 10 to the negative 11. So there you have it. Now we've got our KSP, and now we can embark on to the second part of the problem. I'm going to copy the KSP because it's what's relevant to us when we solve the second part of the problem, and I gave myself some more space over here. So we get that our KSP, and I don't need this, so KSP is equal to 1.6 times 10 to the negative 11. So what's happening in the second part, the KSP doesn't change, but now it's asking you for the solubility of the magnesium hydroxide in a barium hydroxide solution that's already got a pH of 12.60. The pH has gone up, so therefore it's more basic. Therefore, it's going to have more hydroxide ions in it, isn't it? Right? It's going to have more hydroxide ions. We need to calculate the concentration of those hydroxide ions. I'm going to use the exact same strategy. If my pH is 12.60, my pOH is going to be 14 minus 12.60, which is 1.40. Same thing I did on the last slide. I'm going to calculate my concentration of hydroxide, which is 10 to the negative POH, which is 10 to the negative 1.40. When you do that, you get 4.0 times 10 to the negative 2 molar as being the concentration of your hydroxide. Notice that this number, 4.0 times 10 to the negative 2, is greater than this number here. It's quite a bit greater, right? And so these are the kind of things you should be asking yourself on the way through the problem. Does this make sense? Yes, so far so good. So let's write out the same equilibrium expression or same equilibrium reaction. We have our magnesium hydroxide, which is in equilibrium with magnesium ions, plus hydroxide ions. We don't consider magnesium hydroxide as having a concentration. Okay? We don't have any of this at first, but we do have some hydroxide ions, don't we? And we have a concentration of 4.0 times 10 to the negative 2 molar. Now that's not going to change, right? We're going to end up forming some magnesium ions, but the 2x over here is not going to be important because the concentration is so much bigger than our KSP. So we're going to be able to ignore that. And at equilibrium, we're going to have x, and then here we're going to have 4.0 times 10 to the negative 2. So now we can do the same thing. Our KSP is equal to the concentration of our magnesium ions times the concentration of hydroxide to the power of 2. The concentration of magnesium, or sorry, my KSP, I'll put that in first. My KSP was what? 1.6 times 10 to the negative 11. It's going to be equal to x multiplied by 4.0 times 10 to the negative 2 squared. So x is going to be equal to 1.6 times 10 to the negative 11 divided by 4 times 10 to the negative 2, all of that squared. And I get the x, which is equal to the solubility of my magnesium, is equal to 1.0 times 10 to the negative 8 molar. And there you have it. And you see that it's dropped, right? It's dropped from, what was it originally? 1.6 times 10 to the negative 4 molar. Okay, so it went down dramatically. Why? Because I already had some hydroxide ions in there. And so it makes sense that the concentration of this is going to have to drop in order for KSP to be satisfied. All right? Give me a thumbs up if you follow me on that one. If you're not sure, or if you have a question, feel free to stop me. Is anybody with me on that one? Okay. All right, just taking some of the concepts that we've already looked at. The barium is a spectator ion because the barium is not involved in the KSP, right? The KSP for this equilibrium only involves magnesium and hydroxide. The barium has nothing to do with it, okay? So all you need to be concerned with is the hydroxide that comes from the barium hydroxide. Does that make sense? Or does that help? Okay, good. Thanks, Brogan. Good. All right. Again, always feel free to stop me and ask me a question. And if I should know the answer, and if I don't, I'll just Google it, right? Just like everybody else. Okay, anyhow. Let's see here. Let's move on from there. And let's talk about Lewis acids and bases. Now, if you remember, in the acids and bases section, Mr. Dion couldn't help himself. And you probably remember that I started out with the Arrhenius definition of an acid and a base, right? And for Arrhenius, an acid was something that when you put it in solution, it made H plus or H3O plus, same thing, okay? But it produced acid. And then Arrhenius said that a base is something that when you put it in water, it makes hydroxide, right? So acids would be things like HCl, the base would be something like sodium hydroxide, for example. And then we came along and we said Bronsted-Lowry, and we said that, and he said, or they said that an acid was an H plus donor, right? And a base was an H plus acceptor. All right, so we broadened the definition. Again, a proton donor would be something like HCl, but a base being a proton acceptor explains why something like ammonia is basic, even though it doesn't have hydroxide in it. And Lewis acids and bases, and again, I couldn't help myself in the last chapter. I went over Lewis acids with you, and we're going to cover them in more detail here. And Lewis said that an acid is an electron acceptor, and that a base is an electron donor. Okay, so a Bronsted-Lowry acid-base reaction simply represents a subcategory of Lewis acid-base reactions, specifically those in which the acid species would be a proton, right? So you can see how H plus is an electron acceptor, right? Okay, so we're going to talk about Lewis acids and bases even more in this section. And you can see how, again, the Bronsted-Lowry model only works when we have a proton transfer. And so the Lewis model is less restricting, right? I just told you that the Bronsted-Lowry acid-base reaction is just a subcategory of Lewis acid-base reactions where a proton is a Lewis acid because it accepts electrons. And we'll look at an example of that, and I'm sure you could all come up with 10 examples of your own. So if we look at what's going on here, we have a reaction between fluoride. So here we have a fluoride ion, and then this is called boron trifluoride, right? You guys are rock solid on your nomenclature. So here you have boron trifluoride and fluoride ion. And the reason why the Lewis base donates a pair of electrons and the Lewis acid, the boron trifluoride, accepts them is because boron is the fifth element in the periodic table. If you look at the electron configuration of boron, right, boron is a second period element. It's 1s2, 2s2, 2p1. So it can fill up the p orbital by taking on extra electrons. Another way to think about it would be this. If you look at the boron here, it doesn't have an octet, right? Incomplete octet. Okay, it doesn't have an octet. Whereas if you look at the boron in the acid-base adduct, which we sometimes call a coordination complex or a coordination adduct, it's got different names. Anyhow, you see that in here, it's surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. And so the boron in the acid-base adduct does have a complete octet of electrons, like that. Again, the Lewis acid is our boron trifluoride, right? It's accepting the electrons from our Lewis base, which happens to be the fluoride ion here. A coordinate covalent bond, or what we sometimes call a dative bond, occurs when one of the atoms in the bond provides both bonding electrons. Okay, so both of the electrons in a sigma bond, both of them come from one atom. For example, a coordinate covalent bond occurs when a water molecule combines with hydrogen to form a hydronium. So you see that the water molecule is donating both of these electrons, right? We could draw an arrow to show the flow of those electrons to the proton, which is behaving as an electron acceptor, a Lewis acid, okay? A coordinate covalent bond also results when an ammonia molecule combines with hydrogen, a hydrogen ion, to form an ammonium ion. So the same thing here. The lone pair on the nitrogen in ammonia, right, gets donated to the proton. So you see how the hydrogen ion or the proton is the electron acceptor. It is the Lewis acid. Okay, and you see how both water and ammonia are the electron donors or Lewis base. And you can be sure that on your next exam, I'll ask you, is this a Lewis base or is this not a Lewis base, things like that. Okay. All right. Well, reactions that involve the formation of coordinate covalent bonds are classified as Lewis acid-base chemistry. Okay. The species donating the electron pair, again, is the Lewis base. and the species accepting the electron pair again is the Lewis acid. Well, we have many different molecules that can behave, or many species that can behave, a molecule or an ion, as a as a Bronsted-Lowry base. And many of those can also behave as a Lewis base. For example, ammonia. We saw how ammonia is a Bronsted base, right? It can accept a proton, but it can also behave as a Lewis base, an electron donor. All right. And you see that what's happening here is that each of these two ammonia molecules, which are Lewis bases, are going to donate a pair of electrons to a silver ion, which is behaving as a Lewis acid. And we get this Lewis acid base adduct here. And the Lewis acid base adduct shown down here is just defined as a compound that contains coordinate covalent bonds, again, which we sometimes call a dative bond. And those bonds, these ones here, formed between the Lewis acid and the Lewis base. And so again, the importance of the Lewis acid base theory is that that model, the Lewis acid base model, greatly expands the number of species that can be considered acids. Now again, when that Lewis base, like ammonia, if we have two molecules of ammonia that react with a silver ion, that adduct that results, we call that a complex ion. Sometimes we call it a coordination complex. It depends on where you read. Okay, so a complex ion or a coordination complex is where we have a central atom, which is typically a transition metal cation, and it's surrounded by ions or molecules that we call ligands. So the ligands here, again, is the Lewis base ammonia in this specific case. Okay, other examples of ligands are things like water is oftentimes seen as a ligand. Also, ions like cyanide or hydroxide come up pretty often as ligands. Again, the reason why they're Lewis bases is because they donate a pair of electrons to the central atom. Okay, there we go. So, coordination complexes, coordinate covalent bonds, Lewis acids, Lewis bases. What else? Ligands. These are all things that you need to be aware of moving forward. Well, what about equilibria with respect to these coordination complex or these complex ions that are formed? I know that in the slides I put complex ion. I grew up when I did my undergraduate, so when I was where you are, I spent a lot of time with instructors that called them coordination complexes. So I tend to use that a little bit more in my speech, but it means the exact same thing as a complex ion. Well, if we look at the interaction between a copper 1 ion with two cyanide ions, we form this interesting coordination complex here. The formation constant is the equilibrium constant for the formation of the coordination complex directly from these ions, right? The metal ion and the ligands in this case, which happen to be a cyanide. Okay. Well, you can imagine that if you have something that's positive and negatively charged, these are going to have a strong attraction for each other. And so unlike KSPs, which are really tiny numbers, right? You look at some of these KSPs, 10 to the minus 15 and things like that. Well, formation constants, or KFs, are going to be really big values. Now, really big numbers. And where would you find KF values? If you're doing any of the practice problems that I recommended from the chapter, you might see questions where they don't give you a KF and you need a KF, you would go to Appendix K. So you could just go down to Appendix K and look up some KFs. The higher the KF, okay, the greater the stability of the complex. All right, the greater the stability of the complex if we have a greater KF. Now, how would I write an expression for KF for this coordination complex that we saw on the last slide? Well, everything is aqueous, right? Everything's an aqueous ion, and so they're all going to be included. Remember, in equilibrium expressions, we include anything that's aqueous or in the gaseous phase, and so here's our KF. Now, if we look up the KF, now I just copied and pasted this straight out of Appendix K, you see that it's a big number, 1 times 10 to the power of 16. So at equilibrium, most of the copper is going to be complexed with the cyanide ions to form the coordination complex, and you're going to have very little copper and cyanide ions left over. Now, the inverse of the formation constant is called a dissociation constant. And the dissociation constant is simply the inverse of the formation constant. So Kd is going to be equal to Kf to the -1, or the reciprocal of the formation constant. Again, if you take this expression right here, or this reaction right here, and you flip it around, okay, you end up with the equilibrium that describes the dissociation, right? So the dissociation constant is the equilibrium constant for the decomposition of the complex. So that means that KDs are going to be really, really small numbers, right? If KF for CuCN2 minus 1 is equal to, go back here, 1 times 10 to the power of 16 times 10 to the power of 16. That means that Kd is going to be equal to 1 over the Kf, which is going to be equal to 1 over 1.0 times 10 to the power of 16. If you take your calculator, hopefully by now you've learned how to use the inverse function. If you take 1 times 10 to the -16, you use the inverse function, you end up with 1.0 times 10 to the -16. And so the Kd is going to be a really small number, whereas the Kf is a really big number. So with that in mind, let's try a practice problem that kind of gets us started here. And it says, calculate the concentration of the silver ion in a solution that is initially 0.10 molar with respect to Ag NH32 positive. Now that is a coordination complex we already saw today. If you go back a couple of slides, you see the interaction between 2 molecules of ammonia plus the silver ion. Again, the ammonia is the Lewis base. The silver is the Lewis acid. Then we form this coordination complex. Okay. If we go back here, go back, how many slides? Right here. This is the coordination complex we're looking at. Okay, so instead of me writing out the Lewis structure for everything, I've just written out the condensed molecular formulas. So we have our ammonia. It's going to be in the solution. This ion is going to be in solution, and this ion is going to be in solution. They're all ions. Okay. Well, if I want to use an ice table to determine the concentration of silver ion that's initially present in this equilibrium, I'm going to use my Kf, right? Because the way I have this reaction written, or this equilibrium written, I should have used Equilibria arrows, sorry. Our Kf is going to be equal to the concentration of Ag NH3 2 cation divided by, maybe I'll put the cation first, the silver ion times the concentration of the ammonium ions squared, like that. Now let's make an ice table. We know that initially we don't have any of these, but we have 0.10 molar of the coordination complex. So that means some of that is going to dissociate to form silver ions and ammonia. Okay, so that means that at equilibrium we're going to have 2x for our ammonia. We're going to have x as the concentration of our silver, and we're going to have 0.10 minus x. We're going to ignore the x in this case. And the reason why is because in this case, the concentration of our coordination complex is so much smaller than the Kf. And so we can ignore the x in this case. So we're going to cross this out, and we're going to write our Kf is going to be equal to 0.10 divided by x times 2x squared, right? Because the ammonia is 2x, so that means that our Kf is going to be equal to 0.10 divided by 4x cubed, which again is equal to our Kf. Our Kf, which isn't given to us here, is 1.7 times 10 to the power of 7. Where did I get that Kf value? I got it from appendix K. Is that where it was? I get all my appendices mixed up here. Yeah, from appendix K. So I've already gone and looked that up. So it's going to be equal to 1.7 times 10 to the power of 7, like that. Now all I have to do is solve for x. So I get the x is going to be equal to the cube root of 1.7 times 10 to the power of 7 divided by, oh, I made a mistake here. So it's 0.10, sorry. 1.7 times 10. There we go. I'll just do it like that. So my x, which is going to be equal to the concentration of my silver ions, it's going to be equal to, I need to do this one. You guys can check my math here, divided by 4 times 1.7 times 10 to the 7. And you get this, and then you take the cube root of it. There we go. And I ended up with 1.1 times 10 to the negative 3. 1.1 times 10 to the negative 3 molar as being the solubility. All right. Now, if you are unsure about the assumption that we made here, we can always check that out. So if we want to check our assumption, right, is x less than 5% of the 0.1? We just take 1.1 times 10 to the negative 3. We divide it by 0.1. We multiply by 100%, and we get 1.1%. Therefore, our assumption was okay. All right, it's less than 5%, and so the assumption is valid. Somebody asked me on a test, are you going to give us these values? I assume you're talking about Kf. Absolutely. There's no way to solve this problem unless you have the Kf. Now, I could ask you a question where I ask you to solve for Kf, but the answer would be, I'm always going to give you enough information to solve any problem. I'm never going to leave you, missing, some part of the information or something like that. Before we move on and look at more content and move into coupled equilibria, I just want to demonstrate one thing to you very quickly. Okay, we solved this problem using the Kf. Now we looked at a Kd as well, right? We talked about Kf and Kd, and we said that Kd is going to be a really small number. So what if we were to try to solve this problem using the Kd, right? We know that Kd is equal to 1 over the Kf, which would be equal to 1 divided by 1.7 times 10 to the power of 7. And so our Kd would be equal to 5.9 times 10 to the negative 8. Right, that's the Kd that represents the dissociation of this ion. So if we have our AgNH3, 2 cation, and it dissociates into silver ions plus ammonia, are we going to get the same answer? Does anybody know? Would this work? If I was to make an ice table using this, I say I start out with 0.10 molar of my coordination complex. Can I use Kd to solve the same problem? I like your answer, Luke, okay? I like your answer a lot. He says, it should, which means, what Luke means is it's going to work if you do it right, and he's 100% correct. Now, if you don't believe me that you can solve this problem using Kd, it's the same thing that when we looked at buffers, right? Remember, we were always able to solve for concentration. You can use Ka or Kb, it doesn't matter. You just have to have the equilibrium set up correctly. So watch, we can solve this using Kd and we should get the exact same answer. If we assume we have none of these, we're going to have a change. We're going to lose some of this. We're going to form some of this, and we're going to form some ammonia. At equilibrium, if we assume we still have 0.10 x and 2x, the Kd is going to be equal to the concentration of silver ions times the concentration of ammonia squared divided by the concentration of my coordination complex. Okay, so we get that our Kd, which is 5.9 times 10 to the negative 8, is equal to x times 2x squared divided by 0.10, which is 4x cubed divided by 0.10. So we simplify that to x cubed is going to be equal to 5.9 times 10 to the negative 9 divided by 4. So we take the cube root. Anyhow, you end up with x being equal to the concentration of the silver ions, and it's equal to, looky, 1.1 times 10 to the negative 3 molar. And so, again, and we could do the same check. We're going to get the same answer. So you can solve these problems using the Kd as long as the equilibrium is set up showing dissociation, or you could solve it using Kf as long as you're showing the formation of the coordination complex. Again, this is an exercise that we could have done way back in chapter 14. We could have done it in chapter 13, okay? But I had a student asked me a question like, can I use, Ka or Kb to solve, this equilibrium? And the answer is yeah, depending on how you set up the ice table and how you look at the equilibrium. All right, so either way would work in this case. Anyhow, there we go. So let's move on to what are called coupled equilibria. We looked at coupled reactions a little bit earlier on in the class. I just want to go over this with you kind of, not quickly, but I just want to take a quick peek at it, I guess. And then I want to try some more problems that deal with KSP today. And then we'll look at some coupled equilibria and what my expectations are in terms of coupled equilibria for you on Friday. So basically on Friday, I want to go over the questions or a few questions that deal with coupled equilibria to kind of give you an idea of where you need to be with coupled equilibria. So in a nutshell, sometimes you can't just have one equilibrium expression to describe a process. You've got to have a couple of them. That's why they're called coupled equilibria. There's some examples that are shown here, okay? Hold on, let me check something quickly. My computer is doing something funny. Yeah, just give me 1 second, you guys. I'm having a problem here with my computer. Just give me a couple of minutes. Technical difficulties. Just let me double check something. Come on. Okay, here we go. I think I fixed it. Okay, can you guys see my new slide that shows aluminum hydroxide on it? This here, can you see where I circled in green?
Yes, sir. Yeah, we can.
Okay, good, thanks. Sorry, I don't know why, but I had fixed up some of these slides and made some changes that I thought would help you understand the concept better, but for some reason, they didn't save correctly to my iPad. So here we go, back to it. Um, yeah, where was I? I said that, you know, there's cases, and this is what section 15.3 is about. There's cases where you need more than one equilibrium expression to describe a process. An example would be if you tried to dissolve aluminum hydroxide by complex ion formation. If you're like, what the heck is that? The idea is this. Aluminum hydroxide is a pretty darn insoluble compound. So you might be wondering, like, is there a way I could get more of it to dissolve in a solution? And the answer is yeah. And the way you do it is by forming a complex ion. What do you mean, Mr. Dion? Let me show you. Okay. If you take aluminum hydroxide, which is miserable, okay, it's like brick dust. It's really insoluble. You want me to prove it to you? Look at the KSP, 10 to the negative 32, my friends. Is that insoluble or is that insoluble? It's like, Chandler Bing. Could you be any more insoluble, right? It's super insoluble. Okay. So how would I get more of it to go in solution? Well, the answer is I'm going to take advantage of Le Chatelier's principle. I'm also going to take advantage of the fact that aluminum, the aluminum cation can form a coordination complex, which has a really stinking high Kf of 1 times 10 to the positive 33. So if I take my aluminum hydroxide and I have very little aluminum ions in solution, but if I jack up the concentration of hydroxide, how would you do that? By adding sodium hydroxide or another strong base. Okay. As my student asked a few minutes ago, you mean the sodium doesn't count? Well, it doesn't have anything to do with these equilibria here. So if you just increase the concentration of hydroxide, if you jack that up, then you're going to end up forming this coordination complex, which has a really high Kf, right through the roof. So overall, what's the result? Is that when you tally up these two expressions right here, right, you add them together, what's going to happen? These three hydroxides are going to cancel, and so will one of these, right? The aluminum ion is going to cancel out. And so overall, the result is you're adding aluminum hydroxide, you're jacking up the concentration of hydroxide, you make the coordination complex. What's that going to do? When you evaluate K, if you're adding two equilibria together, the K is going to be the product of these two Ks, right? So it's the KSP multiplied by the KF, which gives you a big number, right? It's greater than 1. Therefore, the equilibrium is going to lie hard to this side. And so now I know what you're thinking. I know some of you who are really astute are saying, well, yeah, Mr. Dion, you're getting more of this to go into solution, but it's not just aluminum and hydroxide anymore. You're right, it's not. But the net effect is that you're solubilizing or you're putting more of this, what you started out with, right? More of it is in solution. Okay. That might have been an even more involved explanation than you needed for a lot of you. But again, the net result is all you're doing is cranking up the amount of hydroxide, forming the coordination complex, and overall, that has a highly favorable or a favorable equilibrium. All right. Does that give me a thumbs up if at least the concept makes sense? You're like, you haven't showed me anything with numbers, but at least the idea is there. Is that there for some of my students? Yes, good. Okay. Just want you to understand what the hell is going on, before we really get into the nuts and bolts of it. Okay. How could we dissolve a precipitate using a strong acid? Well, you all know that when you take a strong acid, you put it in water, it's going to produce some hydronium. Okay. Well, what can hydronium do? We spent enough time in the acids and bases chapter that you all know that a hydronium ion can react with an anion. Like what? Like maybe a hydroxide? Well, heck yeah. Hydronium is going to react with hydroxide just to produce water, Mr. Dion. I know that. Great. Okay. So hydronium could react with an anion like a hydroxide or an ammonium or an ammonia of a complex, right? Because an acid can react with ammonia to form water in the ammonium ion. Okay, good. So we can take advantage of that to dissolve compounds that would otherwise be insoluble or relatively insoluble in water. So what are the types of compounds that tend to have an increased water solubility in the presence of a strong acid? First of all, if you've got a hydroxide as your anion, well, yeah, then it's going to dissolve even more. We're going to take a look at that on the next slide. So give me a second. We'll look at a good example of that. Also, what if you have an anion that's a weak base? Or what if you have an ion in a complex that's ammonia? Well, we already talked about ammonia. Ammonia can react with acid. Everybody knows that. But what if you have barium fluoride? This would make a really easy multiple choice question. If I said, which one of these ionic compounds is going to be more soluble in an acidic solution? You want me to tell you how you know the answer? Because if the anion is a weak base, right? If you have an anion that's a weak base, what's it going to do? It's going to react with the acid. So that's why something like barium fluoride, right, which is made from barium cations and fluoride anions. Well, fluoride is a weak base. How do I know it's a weak base? Okay, it's not a strong base, right? It's not a strong base. It's not hydroxide. It's not one of the strong bases that we looked at. It's the conjugate base of a weak acid. Okay, so that means that the acid is going to react with the fluoride to make HF. Now, if we compare, if you're really confused, if you're like, okay, I'm not sure about the whole weak base thing, we'll just evaluate the stability or the strength of these two acids. Hydronium is stronger than hydrogen fluoride, and so the equilibrium is going to lie to this side. It's going to lie to the side of the weaker acid. Okay, so again, if you've got an anion that is a weak base, it's going to react with an acid. All right, there we go. Here's that example of an acid reacting with a hydroxide anion. Let's say you have some zinc 2 hydroxide. So that's this compound right here. What happens when you put zinc 2 hydroxide in a strong acid solution? Well, first of all, it's an insoluble compound, but it's going to give you some zinc and some hydroxide. But what if we put it in strong acid? Well, the acid, which we have drawn here just as H plus instead of H2O plus, can react with the hydroxide to form water. Let's take a look. If we tally those two up, what do we get? We get those hydroxides canceling, and we see that the net result is this, that when you put zinc hydroxide, which again, stubborn compound, insoluble, okay, but if you put it in acid, the acid is going to react with the hydroxide, and the net effect is that more of it is going to go and get dissolved, okay? That's the whole idea behind coupled equilibrium. So again, we can explain this in terms of Le Chatelier's principle, okay? Because we have a reaction between the hydroxide and the acid to form water, we're essentially removing hydroxide from here, right? Again, if you're like, what the heck are you talking about, Mr. Dion? All I'm saying is if you just look at this reaction right here, I'm actually trying to make it simpler, okay? If you're confused. If you add acid, what's it going to do? It's going to destroy this. If you lower the concentration of that, it's going to push the equilibrium in this direction to produce more of it and reestablish the KSP. That's all that's going on here in this coupled equilibrium. Here's an example of a Lewis base dissolving an ionic compound here by the formation of a coordination complex. So similar vein here, if you look at the zinc hydroxide, okay, so now instead of using a strong acid, we're using a Lewis base, meaning ammonia, to increase the solubility of the zinc hydroxide. So again, here's our zinc hydroxide. This time I put in the KSP. It's really low. It's highly insoluble. What happens if you throw some ammonia in there? Well, the KF for the formation of this zinc and ammonia cation is really high. Look what happens when you add those two equations together. You cancel out the zinc ions like that. So the net result is this, that when you take the zinc and you hydroxide and you put it in ammonia, you end up dissolving more of the zinc hydroxide, right? The equilibrium is going to lie harder to this side. right? The new K is going to be equal to the product of the KSP times the KF. If you take your calculator and you take 4 times 10 to the negative 17 and you multiply it by 3.6 times 10 to the power of 8, you get 1.44 times 10 to the negative 8. You're like, oh, come on, Mr. Dion, that's not a huge number. That's not big. That's not 22 like it was a few slides ago. Yeah, but it's a hell of a lot bigger than this, right? And so you can see how the formation of that complex ion is helping dissolve the ionic compound. Give me a thumbs up if you follow me on the idea of just assisting in the dissolution of an ionic compound by the addition of an acid, what we saw in the last slide, or ammonia, right, a Lewis base here, to form a complex ion. It's the same rationale both times. Thanks, Bruna. Excellent. Excuse me. Okay. Now, I know that some of you are obsessed with your grades, and that's a good thing. Okay, it's good to give a damn about your grades. I want you to. But if you're rifling through your mind saying, what the hell is he going to ask about this? Do I have to add all these things together? Like I said, next class, I want to spend more time going over the type of questions that I expect you to be able to nail with respect to these. So I only want to look at one of these today, and then I thought we would actually go back and look at more problems. Oops. More problems to deal with this. Just give me uno segundo here. There's something I want to tell you guys. Sorry, normally I'm very organized, but I don't know if my kids were down here or what. Well, anyway. All right, let's take a look at this problem here. Let me grab my calculator again here. And you can probably see, if you looked ahead in the slides, I put the answer to this one in here. But I wanted to work it out here with my students. It just says, calculate the molar solubility of silver chloride in a 1 molar ammonia solution. Well, if we think about silver chloride, and I'm sure some of you have made silver chloride in the lab, you would have combined maybe silver nitrate and sodium chloride, and you see a white precipitate. That's silver chloride that's formed. Well, if we look at the dissociation of silver chloride to form silver ions and chloride ions, there's a KSP associated with that, right? The KSP is going to be equal to the concentration of silver ions times the concentration of chloride ions. And that KSP, which again, I would have to give you, I'm not going to ask you to memorize a bunch of KSPs, that's ridiculous, is 1.6 times 10 to the negative 10. So again, you could look that up in Appendix K if you want. All right. Well, what about silver ions, right? Because we know that a silver ion is a Lewis acid, and we know that an ammonia molecule is a Lewis base. Well, what if I had silver ions, okay, silver ions, sorry, and they reacted with ammonia? And if you're saying, Mr. Dion, didn't we look at this already 2 times today? Yes. Okay. Then we can form this AgNH3 2 ion coordination complex. That has a Kf being equal to 1.5 times 10 to the power of 7. Now, what if we tally these two up? If we add these two together, we see that the silver ions cancel out, and we're left over with this expression, that silver chloride in the presence of ammonia is in equilibrium with the coordination complex. Oops, there we go. Plus a chloride ion. And the K for this process is going to be the product of the two Ks, the KSP times the KF. Now I've already gone ahead and multiplied those two together, and you get that your K is equal to 2.4 times 10 to the negative 1. You could also say that your new K is equal to, did I leave aqueous out over here? Sorry, getting ahead of myself. There we go. So everything's aqueous. We could also say that our K is equal to the concentration of the coordination complex ion multiplied by the chloride divided by, divided by the concentration of our ammonia squared, right? We leave out the silver chloride because it's a solid. So now we've got our new K and we have our K expression. Now we're ready to set up an ice table. So what I'm going to do is I'm going to, I don't know, I'll just move on to the next slide and write it all over again. So we have our silver chloride plus our ammonia, which is in equilibrium with the coordination complex ion plus chloride. We know our new K, which is 2.4 times 10 to the negative 1. Okay? We know that initially, we don't worry about the concentration of a solid. We're in 1 molar ammonia, so we have 1.0 moles per liter of this. We're going to say we have none of these. There's some kind of change where we're going to lose a certain amount of our silver chloride, right? That's what we're trying to determine, is the amount of this that's going to dissolve. Now, if we lose X here, since the ratio is 1 to 2 for my silver chloride to my ammonia, I'm going to lose 2X here. I'm going to gain X here, and I'm going to gain X here, like that. So that means that at equilibrium, again, I don't worry about the concentration of silver chloride. I have 1.0 subtract 2X. I have X, and I have X here. Now, if I use my same equilibrium expression that I used on the last slide, I'm not going to rewrite it out again, and I'm talking about this right here. I'm going to have that my K, which is equal to 2.4 times 10 to the minus 1, is going to be equal to X squared divided by 1.0 subtract 2X and all of that squared. This one is easy. You don't even have to worry about an assumption because you can avoid the quadratic really easily on this, right? All you'd have to do is take the square root of both sides of the equation. And when you do that, you end up with the square root of 2.4 times 10 to the negative 1. You take the square root and you get, where's my black pen? You get 4.9 times 10 to the negative 1 is equal to X over 1.0 minus 2X. That's the part I skipped, but anyhow, I did solve for X, and when you do, you get that your X is equal to 0.0045 molar, like that. And so that is the molar solubility of your silver chloride. That's the amount that's going to dissolve. So you can see that it's a lot more than would dissolve if you just used the KSP. If you don't believe me, you can check it out, and you can see that it's a lot higher now. So what did we do? We had to couple these two equilibrium expressions together to get overall what happens when you put silver chloride in ammonia. Well, we figured that out. Okay, you get the coordination complex plus the chloride ion. We figured out what the new K is. The K is a lot higher than the KSP of silver chloride itself. That gives you a pretty darn good hint that you're on the right track, right? Then we made an ice table and we used our K expression. This one we were able to avoid the whole idea of a quadratic and having to make any assumptions. We can just leave all that out because we were able to take the square root of both sides and we solved for the molar solubility of X just like that. So it's Wednesday, it's 10:23. What I had planned, and again, I have the solution in here, but I wanted to work it out with you, is I wanted to try a couple of problems where I would give you guys the opportunity to spend a couple of minutes trying a problem yourself. I know I don't do this very often in class. It's because I like talking to my students. I have a really difficult time being quiet. And over Microsoft Teams, it's worse because at least if we were together in a room, I would let you all work on a problem, but then I would run around like a maniac and see what you're all doing because I'm very interested in what my students are doing. But I would like to give you, it's really difficult for me to do this, but I'm going to give you 2 minutes to try this problem. Okay, based off of everything you know, this isn't involved, or this question is not about coupled equilibria. Okay, it's just about KSP. And let's read the question together. It says the pH of a saturated solution, right? So that means, you know, saturated solution. You can think of KSP if it's saturated, right? You know the pH of the nickel hydroxide solution. It's 8.85. I want to see if you guys can calculate the KSP. Please do not look at the answer. Give it a try for yourself. I'm going to give you 2 minutes to think about it. And then I'm going to come back. I'll actually step out and take a drink of water. And if you think you have the answer, if you want to type it in the chat, be my guest. Again, you'll probably have to make an ice table for this. I would, because I'm the instructor. But again, I'm going to give you a couple of minutes to give it a try. Hey, all right. You guys, Jamil, you caught me. I was just getting ready to say, does anybody have an answer? Jamil, did you use an ice table to solve the problem? I'm curious. Okay. Yeah, that's good. Okay. So I asked him if he used an ice table, and he says, yes-ish. I kind of did it mentally. Okay, there's no problem with that at all. Did anybody else do it without an ice table? I'm just curious. I'd like to know where my students are at. I mean, I'm probably going to keep using ice tables, but that's as an instructor. Okay, great. Thanks, Joey. Excellent. What did Violet say? Sorry. Okay, great. Okay, seems like most of my students are using ice tables. Okay, so I'd say if you are confident, and I mean really confident, that you can solve it without an ice table, that's cool. I don't have a problem with that. If you can actually work the ice table out in your mind, there's no problem with that. However, if you're not 100% sure, I would always use an ice table to solve these kinds of problems. Okay, I just want to put that disclaimer out there. I just wouldn't want you to mess something up because you tried to do it too fast. Okay. All right, let's take a look here. It says you got a saturated solution of nickel hydroxide. You've got the pH. And it's asking you to calculate what the KSP for nickel hydroxide is. Well, look, if we just start out with the equilibrium, okay, if you have nickel hydroxide, which is an insoluble compound, it's going to be in equilibrium with nickel 2 ions. So I should call it nickel 2 hydroxide, but anyhow, so you get the nickel 2 ions plus 2 hydroxides like that. And you know that the KSP is what you're looking for. But KSP is going to be equal to the concentration of the nickel ions times the concentration of the hydroxide ions squared, like that. Okay, sounds good. All right, well, if we start out with a certain amount of nickel hydroxide, right, we're going to form, initially, we're going to have none of this and none of this, but then we're going to lose some of that nickel hydroxide is going to dissociate to form some nickel ions and twice as many hydroxide ions, so that at equilibrium, we have a certain concentration of nickel ions, but we've got twice the concentration of hydroxide ions, right? But we can figure out what the concentration of the hydroxide ions are, can't we? We can figure out what 2x is equal to because we know that if the pH is equal to 8.88, 8.85, we know that the pOH is going to be equal to 14 minus 8.85, which is 5.15. So that means the concentration of hydroxide is going to be equal to 10 to the power of negative 5.15. We get that the concentration of our hydroxide is equal to 7.1 times 10 to the negative 6 molar. Right, now we've worked that out, but we know that that's equal to 2x. So that means that x, which is equal to the concentration of our nickel ions, is going to be equal to 7.1 times 10 to the negative 6 divided by 2, which gives you 3.6 times 10 to the negative 6 molar. Now we have everything we need. We've got the concentration of hydroxide, we've got the concentration of nickel ions, and we have our KSP expression. And so we write that KSP is going to be equal to 3.6 times 10 to the negative 6 multiplied by 7.1 times 10 to the negative 6, and you square the whole thing, and we get that KSP is going to be equal to 1.8 times 10 to the negative 16. Can make a nicer 6. There we go. And there's our KSP. I would consider this, and I know that I don't like to gauge problems for my students and air it out publicly and say, oh, this is a difficult problem, this is a easier problem. I would say that this would be a pretty standard, basic problem on KSP that everybody should be able to do. Give me a thumbs up if you follow me on that. I want to make sure that my students are with me on this problem. Give me a cha or a na. Okay, thanks, Ben. Good. All right. Let's take a look at this one here. Let's try one more and then maybe we'll call it a day. Okay. Brogan, is there something in particular? Brogan, did you write something?
Sorry, my computer's super delayed. That was from like 30 minutes ago.
Oh, okay. All
Sorry.
right. So, Brogan, are you still there?
Yes.
Do you follow me on this problem? Are you?
Yes.
Okay, good. All right. Wonderful. Excellent. Well, let's try another one. This is question number 2. This is from the additional problems. It just asks for the molar solubility in grams per liter, right? As long as you have it in grams per mole and you know the molar mass, of course you can figure out the solubility in grams per liter pretty quick. Okay, so we are given the KSP of silver sulfate, so let's go for it. We know that if we have some silver sulfate, Ag2SO4, it's a solid. It's going to be in equilibrium with twice as many silver ions as I have sulfate ions. I'm imagining that by this point of general chemistry 2, you're all pretty rock solid in your polyatomic ions. So you have a certain amount of this. You have none of these to start with. You're going to lose some of this. You're going to gain twice as many silver ions as you will sulfate ions. And then at equilibrium, you're going to have twice as much silver ions as you do sulfate ions. The KSP is equal to the concentration of the silver ions squared times the concentration of the sulfate ions. We know that our KSP is 1.2 times 10 to the negative 5. It's going to be equal to 2x squared times x, which is equal to 4x cubed. And so x is going to be equal to the cube root of 1.2 times 10 to the negative 5 divided by 4. And we get that x is equal to the molar solubility in moles per liter, which is 1.4 times 10 to the negative 2 moles per liter. Well, if we want it in grams per liter, we're going to need the molar mass of the silver sulfate. Okay, now we could spend all the time, but that's a general chemistry 1 type of thing. So the molar mass of the silver sulfate is 311.81 grams per mole. There we go. And so to calculate the molar solubility in terms of grams per liter, we're just going to multiply by that conversion factor. We have 311.81 grams in 1 mole. And you see that moles cancel. And we end up with the molar solubility in grams per liter. Where's my calculator? We end up with 1.4 times 10 to the negative 2 multiplied by 3 times 8.1. And that gives you 4.4, so you don't have 2 sig figs, so 4.4 grams per liter as being the molar solubility. All right, there we go.